So here we go. This is number 12 on the practice test, and it says use the graphing guidelines to make a complete graph of f. So the things that you want to include would be things like you want to be aware of your domain and range. So you want to think about that. You want to determine any intercepts, asymptotes, and maybe even think about the symmetry of the graph if there's some symmetry that could help us to graph it. And then you want to locate any x values for which the first and second derivative are either 0 or do not exist. So those would be your critical numbers. So locate values where f prime or f double prime are 0 or do not exist. And then you can analyze the first and second derivatives to see where they're positive or negative to determine increasing, decreasing, concave up or concave down once you have that information. So look for increasing, decreasing, concave up, and concave down. The points where the graph changes from increasing to decreasing, of course, are your relative extrema. And then you have inflection points where they change from concave up to concave down. So these are the three main categories of things that we need to think about. This particular function is a rational function. That just means that it's a fraction, a ratio. And with rational functions, in a rational function, when you're finding the domain, the only place that you're gonna have restricted values of x that we're not allowed to plug in, is where the denominator is equal to 0. So whenever you're finding the domain of a rational function, you're just always going to set the denominator equal to 0. So in this case, x squared minus 4 equals 0 would mean that x is equal to plus or minus 2. So those are the only values that we're not allowed to have. So our domain is going to be everywhere from negative infinity to negative 2, negative 2 to 2, and 2 to infinity. And most likely these are vertical asymptotes here. They are vertical asymptotes as long as the fraction cannot be reduced, the rational function can't be reduced to not include them. In that case, it would be a hole in the graph. So in this case, these are vertical asymptotes as well. In the process of finding the domain, we found some vertical asymptotes too. Now, as far as the range goes, for that, we would want to look at some other things like horizontal asymptotes play in. So let's take a look at the limit to find horizontal asymptotes. We're talking about limits to positive and negative infinity. So the limit, for example, as x goes to infinity of this function, which is 9x over x squared minus 4. If that does approach a finite number, then that's going to be a horizontal asymptote, which means that the function is going to get really close to that value as x goes to infinity. And so in this case, there's an algebraic approach, and then there's kind of a shortcut. So in this case, the shortcut way says that when the power of the x in the numerator is smaller than the one in the denominator, then that means that it's going to go to 0. You can think of it as the highest power dominates. In other words, as x gets extremely large, the millions, this negative 4 here is not going to have much of an effect on the value of the expression at all. So this limit is actually going to be the same as the limit of just the ratio of the two highest terms. That reduces to the limit as x goes to infinity of 9x, two highest degree terms, I should say. So as x gets very large, 9 stays the same, and this gets very close to 0. We have a horizontal asymptote, y equals 0. Let's go ahead and start drawing a little bit of this graph, because the thing I like to put on a graph first is the asymptotes, because those are like guidelines for the graph. By the way, the limit to negative infinity for that one would still go to 0 even if the x were a negative value. So that's the only horizontal asymptote. I can't draw dotted lines very easily, so I'm going to use green to represent my asymptotes. So we have a vertical asymptote at x equals 2 and at x equals negative 2. Okay, so there are my two vertical asymptotes. We have a horizontal asymptote at y equals 0, which is the x-axis. Okay, so there's my horizontal asymptote. Let's label their equations. x equals 2 and x equals negative 2 and y equals 0. Okay, we could check for symmetry. I do notice here that it looks like there might be some y-axis symmetry because you can tell how the vertical asymptotes are symmetric. To see if you have y-axis symmetry, we need to check if f of negative x is actually equal to f of x. That's what's called an even function. And so f of negative x is, if we plug that in, we would get 9 times negative x over negative x squared minus 4. Okay, so that's going to be negative 9x over x squared minus 4, which is actually what this means is f of negative x equals the opposite of f of x. And it is actually origin symmetry. So what that means is for every point, say A comma B over here, we would have a point that you could see on the other side of the origin that would be negative A comma negative B. Okay, so that gives us a little bit of an idea of what kind of things are going to go on with this graph. So we'll keep that in mind. Next thing we're going to do is locate some critical values. So we have f of x is equal to, maybe go up a little bit too. F of x is equal to 9x over x squared minus 4. We're going to find f prime. This is something with an x divided by something with an x, so we have to use the quotient rule. So we have f prime of x is going to be the bottom, x squared minus 4, times the derivative of the top. The derivative of 9x is 9, minus the top, which is 9x, times the derivative of the bottom. The derivative of x squared is 2x, and the derivative of negative 4 is 0. So we're just going to get 2x. And then we're going to divide that by the bottom squared. Whenever you use the quotient rule, it's a good idea to try and factor the numerator, and if possible, before you go ahead and distribute. So in this case, I have two terms here and here. And the only thing I see in common there is the 9. So I'll factor that 9 out, and let's see what's left behind. We have x squared minus 4 minus x times 2x is 2x squared. Okay, so that's going to give us, let's see, 9 times, and we have negative 3x squared minus 4 all over x squared minus 4 squared. All right, so we need to know two things. One, where is this equal to 0, this derivative, and where is it undefined? In order for the derivative to be equal to 0, its numerator would have to be equal to 0. Well, nothing can equal 0, but the factor negative 3x squared minus 4 could. So I'm going to add 4. Oops, I made a mistake here. I just realized. That should have been a negative 1x squared. Sorry, not negative 3. Positive 1 x squared minus 2x squared. So that should have been a negative x squared. Okay, so this would mean negative x squared positive 4, divide both sides by negative 1, we get x squared equals negative 4. And that's not going to happen in the real number system. So that means we have no solution there. And then we already know from when we analyzed f that if we set this denominator equal to 0, we're going to get x squared minus 4 equals 0, which means that x is plus or minus 2. Those are where the original function was undefined, and of course the derivative is undefined there as well. We're going to go ahead and make what's called a first derivative sign chart, so I can see where the first derivative is positive and where it's negative. The only place the sign of the derivative can change is at negative 2 and 2, where it's undefined. So we're going to plug in test values in each of these intervals, one less than negative 2, one between negative 2 and 2, and one to the right of 2, to see if we plug it into the first derivative, would we get a positive or a negative? It looks like in this case, if you think about this, factor out a -1, we're going to have -9 times x squared plus 4. X squared plus 4 is actually always positive no matter what I plug into it. And we're squaring the denominator, so that's going to be positive as well. So the -9 times a positive divided by positive, this function is going to always be decreasing on these intervals. All right, so now let's analyze the second derivative, f double prime of x. We're going to have to take the derivative of f prime. So we're looking at this guy over here. We're going to have to use a quotient rule. So we're going to take the bottom, which is x squared minus 4 squared, and then we're going to multiply that times the derivative of the top. The derivative of the top, the -9 stays the same, and the derivative of x squared is 2x. Derivative of 4 is 0. And then we're going to say minus the top times the derivative of the bottom. So -9 times x squared plus 4 times the derivative of the bottom, which is going to require the use of the chain rule. We're going to bring the general power rule. We're going to bring the 2 out front, subtract 1 from it. But then we have to multiply by the derivative of the base, so that's going to be 2x. Now in the denominator, we have the previous denominator squared. So instead of x squared minus 4 squared, it'll be to the 4th power. All right, so here's that step in the quotient rule where you want to look at factoring out whatever's in common as much as possible. This guy here separates the numerator into two big terms. On the left, we have a -9 here, and on the right, we have a -9 as well. So one option would be to factor out a -9. What else do we see in common? Well, on the left, we have the x squared minus 4 raised to the 2nd power. And on the right, we have an x squared minus 4 raised to the 1st power. So we could take that out. The lower of the two. Always take the lower of the two powers. And then on the left, we have a 2x. And on the right, we also have a 2x. So we could take that out. So let's see what's left behind. Okay, so in the first term, we have one of the x squared minus 4's left. And we took out the -9 and the 2x. And then here's the subtraction. And in the second term, we have only the 2 and the x squared plus 4 left. So now we're going to simplify a bit inside of those brackets. So we have x squared minus 4 minus 2x squared minus 8. -18x times x squared minus 4. It's good to leave it factored out though, and because we're going to want to see if we can reduce in a minute. All right, and then x squared minus 2x squared is -x squared. -4 minus 8 is going to be minus 12. We have a factor of x squared minus 4 in the top and the bottom, so we can reduce. So we have -18x times -x squared minus 12 divided by x squared minus 4 to the 3rd. Because we canceled one of these with one of these. And I notice here I have a bunch of negatives running around in the top. I'm going to go ahead and distribute that negative through, not the 18, but just the negative, so we don't have so many minus signs. So that's going to give us 18x times x squared plus 12. And here we go. Okay, so now what we want, remember this is f double prime. This is going to help us find inflection points, which is where it changes concavity. So we want to know where is this derivative, second derivative, equal to 0, and where is it undefined. So it's going to be equal to 0 when its numerator equals 0, which will happen when either 18x is 0 or x squared plus 12 is 0. It's going to be undefined when its denominator is 0, which would be when x squared minus 4 equals 0. If 18x is equal to 0, then x has to be 0. If x squared plus 12 is 0, the only way that can happen is if x squared is equal to a negative number, and we're not interested in imaginary solutions here, so we're working on real valued functions. All right, and then we're going to have x squared minus 4 equals 0, meaning x squared equals 4, so x cannot be plus or minus 2 again. So this time there are three important numbers. that we want to keep in mind. We have when x is 0, when x is -2, and when x is 2, undefined and undefined, and 0 in the middle. So again, we can test points on each of the intervals. -3, -1, 1, and 3 are examples of values we could use. Let's see, plugging into as factored of a form as possible. 18x times x squared plus 12 over, I'm going to think of this as x minus 2 times x plus 2 cubed. So plugging a -3 into the numerator, 18 times -3 would be a negative number, and we would multiply that times, well, x squared plus 12 is always positive. And then in the denominator, we would have a negative and a negative, so negative times negative cubed. So we would have a positive down there. So on balance, negative times positive divided by positive is going to be a negative. Plugging in -1, the numerator would still be a -18 times some positive number. And then in the denominator, we would have a negative times a positive. So that would give us a negative cubed. And negative divided by a negative is positive. So we do have a change in concavity there. And then plugging in a 1, 18 times 1 is a positive times a positive over 1 minus 2 is negative, 1 plus 2 is positive. So we're going to have a positive divided by a negative, which is negative. My apologies. I forgot to find our y-intercepts. So let's go back and do that before we use the sign charts to help us get the shape. Okay, so let's take our function 9x over x squared minus 4 and find its intercepts. These are actual points on the graph that will help us to have starting points when we draw it. So anytime you're asked to find x-intercepts, you're always going to let f of x equal 0. 0 equals 9x over x squared minus 4 only happens if 0 is equal to 9x, which means x is equal to 0. So we have both an x and a y-intercept at 0, 0. Since there can only be one y-intercept, we can stop there. We don't need to actually solve for the y-intercept. We already have it. All right, so that is the only actual point we have found at first for this function. So I'm going to go ahead and plot that 0, 0. And let's go ahead and find one other point on, you see how the asymptotes, they divide the graph up into 3 intervals. The one to the left of -2, the one between -2 and 2, and the one to the right. So on each piece of the domain, it would be nice to have one starting point. So I'm going to go ahead and plug into the function maybe negative. I can't see that it's going to make a huge difference which I pick. So I'm going to do f of -3 is going to be 9 times -3 over -3 squared minus 4. It's going to be -27 over 9 minus 4, which is -27 fifths, so a little bit more than -5. So -3 going to my graph, -3, and then just past 1, 2, 3, 4, 5, somewhere around here we have a point. -3, -27 fifths. Okay, and also without plugging in, since we do know that we have origin symmetry, we also know that on the opposite side, it's going to go through 3 positive 27 fifths, which is going to be somewhere around here. Okay, so now we have at least one point on each of these segments of the domain. And now I'm going to move the first derivative and second derivative sign chart so we can look at them as we graph this thing. There's my first derivative sign chart. Let me grab my second derivative sign chart. On the interval to the left of -2, what we see is that the first derivative is negative, meaning the function is decreasing, and the second derivative is negative, meaning that the function is concave down. So that kind of makes sense though, because this graph is going to want to hug those asymptotes. We're decreasing from left to right. Always think of it from left to right. It's decreasing, and it's concave down like water would spill out of it, right? Remember, concave up looks like this, concave down looks like this. Now, how do I know that it's not going to cross this asymptote, this horizontal asymptote y equals 0? So what a horizontal asymptote is telling you is that as the function approaches infinity, it's going to behave very close to that line, but that doesn't mean that it can't cross it from time to time. And in fact, in this function, it does. We already know that the function goes through 0, 0. But since we solved for where the function equals 0 and we only got that single point, we know it's not going to cross anywhere else. All right, now let's look at the next piece and talk about what its shape would be like. So between -2 and 2, from -2 to 0, graph is going to be decreasing and concave up. And if you're not sure where to start, go ahead and plot another point. Let's say we put in -1 to the function. F of -1 would be 9 times -1 over -1 squared minus 4. It's going to be -9 over -3, which would be 3. But that makes sense, right? That it would be somewhere above the x-axis because we know that at 0 it crosses the x-axis, and up until then it has to decrease down to that value. So let's go ahead and plot 1, 3. And then it's going to, or -1, 3 rather. Then we're going to decrease. Hard to draw those on this tablet sometimes, but I'm gonna try. So it's gonna decrease but be concave up, like it could hold water, something like this. Okay, and then to the right of 0, it's decreasing because first derivative is negative, and it's concave down because the second derivative is negative. So decreasing makes sense. We're just gonna continue going downward towards this other asymptote, and it curves as it does so. So it looks like it's concave down. All right, and now on the third interval, the first derivative is negative, so it's decreasing, and it's concave up because the second derivative is positive. So let's go ahead and draw in that piece. Makes sense that it's decreasing. It's going to go through this point 3/27, so we're going to start a little bit above there. Decreases, and again, we already talked about it's not going to cross this horizontal asymptote any more times. This is a pretty accurate graph of this function that we have here. I hope you found this video useful. If you did, please remember to like it.